Good evening, everyone. I am Mr. Ish. Bernoullis equation, it represents a specific form of a first order differential equation, but these are rather difficult and they're rather tricky to get accustomed to. However, I'm going to break it down for you all in this particular video, showing you the technique with a single example. Then in a few other videos we can do practice of this form. Bernoullis equation is something you want to learn after you've done the linear first order differential equation solving type of questions where you're using the integrating factor, because this builds off that technique. Remember, the previous technique we learned was utilizing the linear first order differential equations, which had this form: dy over dx plus py was equal to q. And you remember this went down the integration factor route. When you have a Bernoullis equation form, you have something which looks like this, but it's dy over dx plus py is equal to q y now to the power of n. The only difference you see between here and this is this specific factor, and this represents the equation form which requires you to utilize and recognize that, and then the subsequent techniques which come from it. Perhaps the best way is for me to show you an example, and we will do by means of that specific example, and I'll talk about the unique steps that come into place for this particular equation form. But remember, this what you know and this what you have to know now. Look right here, we have dy over dx plus y is equal to xy squared. It looks very much like dy over dx plus py is equal to q, except here q has this addition of this factor which is y to the n, and hence we're looking here at a Bernoullis equation, a form for which you can now begin to learn a new technique. So this right here is our question: how do we go about solving this differential equation? That is, finding the equation or the function for which this differential equation is true. You gotta convert everything into the linear first order form by means of steps. Take this y square and divide it across, and look what happens. You'll have 1 over y square dy over dx plus, simplify this, you'll have y to the power of minus 1 is equal to x. Now you've eliminated the y square from here, but you can write this in a good way, and the good way is to write it in this form. Now look at what you have. You've eliminated that y square component. You have basically here something which looks like a q, and that's good. We're on the right track. What do we do next? You have to use a couple of substitutions. A substitution such as the z is equal to, don't understand why you have to do it, just learn that you have to do it, y to the power of 1 minus n. And what is this n? It's exactly this value you're seeing right over here. Z is equal to y to the 1 minus 2, which is y to the minus 1. Now you have to differentiate this. dz over dx is equal to the derivative of this with respect to y. It's minus y to the minus 2 dy over dx. Nothing here new, you don't know how to do, except instead of looking at x, we're looking at y, and we're looking at z. That's all what it is. This right here is perhaps the most essential part of this entire procedure. This has to come now into this right over here. But there's one thing you gotta do. When you come to this step, you have to identify the coefficient right over here. What's a coefficient? It's a minus 1. Multiply everything here by a minus 1 times minus 1, and look what happens. You'll have minus y to the minus 2 dy over dx minus y to the minus 1. Remember, we're multiplying everything here by minus 1 is equal to minus x. Well, we've done that. What do we do next? I'm erasing this just for neatness, and I'm bringing a minus over here. Well, we've done this. Now what do? We bring these substitutions into play. This is one substitution right here, and this right here is another substitution. You fit that into what you see here. I have z is equal to y to the power of 1 minus n, which in this particular example was equal to y to the power of minus 1. Where I have y to the power of minus 1, I can squeeze in a z. Where I see this, I can squeeze in dz over dx, and that's exactly what I see right here. dz, derivative with respect to z, is equal to this, and I am seeing a dz over dx minus z is equal to minus x. Now we have everything which looks like the linear first order differential equation. Now I'm just showing you how it looks like that. It looks like this. This is exactly what it looks like. Yeah, we have z and x. We're not seeing a y, but everything looks in that form, in a linear first order differential form. We got minuses, that's alright, plus minus. I'm not worrying about that, but I'm looking at the general form. Now this right here, from here I'll do the integration factor item. And you always look at the coefficient right here, your p. Remember e to the exponent integral p dx, you remember that. What's p over here? It's a minus 1. E to the exponent of integral minus dx, which is e to the power of minus x. Well, here it is, e to the minus x, which will now multiply across right here. And I will multiply it across right here. I'm going to erase this because you know this part. And then we'll multiply it across right here. We'll multiply it here, e to the minus x. When we multiply it across, what do we generate? E to the minus x dz over dx minus e to the minus x z. I can parenthesize, there's nothing wrong with doing that. Is equal to minus x e to the minus x. Now, we have everything over here in the makings of the items we need to take us to our end point. Everything over here comes from a certain derivative, and you know what that derivative is. Look at this and look at this. It's z e to the minus x is equal to all of this minus x e to the minus x. Bring in your integral sign. These cancel out, so you're looking at z e to the minus x is equal to the integral of this minus x e to the minus x dx, for which you have to do integrating by parts. Remember, Bernoullis equation style differential equations require more work. They're more difficult, but that's just the way it is. We've come up to this point right over here. You can integrate this, it's not hard. You have to do series of substitution. U is equal to x, du is equal to dx. V is equal to integral of what remains, which is e to the minus x dx, which right here is minus e to the minus x. You'll bring everything over here. I'm going to work it out for you and I'll bring it right over here. I'll have uv, and remember, don't forget we have a minus sitting outside. This minus can be brought right here. I have a minus, and now I'll do uv minus integral v du. I have a minus uv, which is a minus coming from right here, minus x e to the minus x minus integral v du, which you know is minus e to the minus x du. You can integrate all of this. Open up the parentheses all across. X e to the minus x. The integral of this is minus e to the minus x, which you know this becomes negated. Minus minus becomes positive. You'll have a minus e to the minus x, which when it hits with that minus, you get a positive plus c. Remember, I've done a lot of talk over here as I did the integration, the antiderivative. You can work it out on the side. This right here is right. The minuses affected everything and you came up with this. That right there is right. It's not wrong. Z e to the minus x is equal to everything you see there. X e to the minus x plus e to the minus x plus c. Now you have to solve for z. When you solve for z, we can do that, but again, I need space, and I'm going to use this space to bring in all of that. I'm going to solve for z and take e to the minus x on the other side, and it'll cancel out with a few things. Z is equal to e to the minus x will cancel out with that. I'll just have a x. E to the minus x will cancel out with this. I'll generate a plus 1. And then e to the minus x will attach with this as c divided by e to the minus x, or you can do ce to the power of positive x. And that right there is so close to completion. All you have to do is resubstitute what z was, which is right here, y to the minus 1. Z all along was equal to y to the minus 1 is equal to x plus 1 plus ce to the x. Therefore, y is equal to what? You can do x plus 1 plus ce to the x all to the power of minus 1. And that right there represents the function or the equation for which this differential equation is true. And I'm going to clean out this differential equation by removing these y squares so you know what the original question was. It was dy where dx plus y is equal to xy square. And the question has been completed, but now you see, in this video I'm showing you just a single example, but I'm showing you how involved this procedure is. In the future videos coming soon, we will look at more of this because you have to know this. But remember how it started. We had something which looked like dy over dx plus py is equal to q, except here the q has a y to the power of n component. It looks like this, dy over dx plus py is equal to q y to the power of n, Bernoullis equation. But I divided it everything here across by y squared because I want to look I want to eliminate that y to the n. I want to look like a linear first order differential equation, so I divide everything by y squared. And when I did that, I ended up coming across over here. Then I did the z substitution. You always look at z is equal to y to the power 1 minus n. This right here generates your n value. You plug it in, you have y to the minus n. Then you do the derivative of this and you come up with this expression. You find the coefficient over here, you multiply it across, you generate a new expression. From this new expression, then you can start doing these substitutions. You can do a substitution for z, you can do a substitution for derivative of z, and they fall right in here. Once you do these substitutions, you have now ended up eliminating the Bernoullis equation and convert it into a linear first order form of the form you know dy over dx plus py equals q. Yes, you have minuses instead of pluses, but it's still of that form. From this form, you do your integration factor determination, which then you multiplied across and you've converted into the form that you now know. The integration factor has been incorporated. From here, now you do the derivative determination of the left side, and you do the integration of both the right and the left sides, and you take it all the way through. At the very end, all you gotta do is resubstitute what the z was, and the z is always equal to what you have right here from your very initial step. Perhaps the most important thing you need to remember here is this part right here. Z is always equal to y to the power 1 minus n, and then you also always have to do dz over dx. You're converting a Bernoullis equation into a linear first order form, then you're carrying it through the normal integration factor procedure, whereby at the end then you're resubstituting back for z and bringing in back your y, and that takes you to your completion point. And that's it for this particular video. I know there's a lot of steps involved with this, but we'll slowly break it down for you over the next successive number of practice questions we'll look at after this video. And thank you for watching. Have a good day.